Yeah, ramp CP is done all the time. It's not particularly a deep theoretical thing. I can tell you what is it about. It's a very practical thing. If you, the reason people do it is very practical, and I don't think there's a deep theory associated with it. So let's say I'm not having a constant amplitude, but a ramp of some sort. If you do adiabatic, then it's more interesting. There's some theory behind it. But this is just to say, well, while I was spin locking and maybe over the time of many hours or a day or two, my amplifier power level is drifting. And even though I want my omega-1 to be a certain value and I want them to be matched, if your amplifier output is not stable, then it's better off I have a range so that part of the time I'm always doing it right. That's all. That's the concept. So if you think that the perfect CP amplitude should be something like this, you can say I'm going to do a ramp where the middle of my ramp is where it should be perfect. But if my amplifier power level drifted, I shift to a different part of the ramp and I'm still matching the Harman-Hahn condition. So that's the purpose of doing it. Otherwise, I think when you're truly off, you just don't get very good CP. You still get it somewhat. It's not like it fails completely, especially under magic angle spinning conditions. Well, actually, let's just say under static conditions. All right, let me give you the phenomenological observation. So let's say I'm considering fixed omega-1s on my carbon channel. I know exactly what it is. What's the RF spin lock field strength? And then on the I spin channel, proton, I can in principle think about how my CP intensity polarization transfer will vary in efficiency depending on my omega-1I. The Harman-Hahn condition says when omega-1I happens to be equal to omega-1s, I should get the best CP. Okay, that's all good. They have high intensity. But then when you deviate from it, what happens? Okay, so it drops a little lower, but it's not so bad. Okay, so there's a certain range that this will operate under the static condition. If you're not rotating your sample, rotating mirrors. If you're starting to spin your sample pretty fast, then the situation changes. Then you start to see that the intensity of CP will drop somewhat quickly when you deviate from omega-1s. But when you go to a condition omega-1s minus omega-r minus the spinning speed, you also get some intensity. And then if you go to this, you also get some intensity. So omega-1s plus omega-r. And if you spin even faster, the theory for this, I would go to Beer-Meyer's papers. So if you're spinning quite fast, then you're really better off going sideband matching. So this will be a fast spinning case. It's one omega-1s minus a very large omega-r, and this will be omega-1s plus omega-r. So you get higher intensity. So what is the y-axis? It's the intensity of the signal you're looking at, the S-spin signal. You get better CP transfer by going off, to the sideband matching instead of the Harman-Hahn omega-1s situation. But in the static situation, it works over a fairly broad range. And I think if you want to prove that, you can probably write down, because the way we prove the Harman-Hahn matching and CP, we say I have these wonderful omega-1 squared term. But if omega-1I or omega-1s is slightly different, well, it still works to some extent, just not perfect. So ramp CP is for a practical purpose. Steep ramp doesn't work because then you spend very little time being correct. Unless you say, well, I'm spinning pretty fast. I'm going to do a steep ramp that go from center band to the sideband. Well, then you still have a vast middle where it's not doing much at all. It's not doing transferring the magnetization. So it's not such a good idea. And the ramp CP also does entail that, since your goal is to spend enough time under the correct condition, if you do the CP quite short, let's say for us with regular 10 kilohertz, 15 kilohertz kind of spinning, if I really just want to pick out the most rigid, rock solid portion of an otherwise heterogeneous kind of biological wet sample, then I might say, let's do CP really short. 100 microseconds is enough. I don't want to wait long because I want to bias against those molecules that are moving. Any dynamic molecules would have weakened dipolar couplings. They won't do well with CP, right? They will get filtered out, and that's maybe I want to do that, right? So then I can choose a short CP contact time. And if I'm doing ramping, then maybe it only spends even small fraction of a short CP contact time to be correct. Then that's very difficult. When you do ramping, ramp CP, you want to have a moderately long contact time. And then instrumentation-wise, all of these ramps, piece-wise, kind of doing this, right? So you have to think about what is the digital resolution, what's the shortest you can do. These days, it's not such a big deal. In my afternoon's talk about dynamics studies by NMR, you'll see that CP is one of these elements very much used to filter out dynamic things. You see only the rigid species. I mean, CP is not too limiting, too restrictive, but it is helpful. And when we look at heterogeneous biomaterials such as plant cell walls, where you have coexisting highly rigid cellulose and quite dynamic, matrix polysaccharide, I want to have everything in my rotor, but I don't want to look at them at the same time, right? So this is a very common element to use to selectively detect stuff. Okay, so let's say for CH bond of 20 kilohertz or so, close enough, 23 kilohertz, the inverse is 50 microsecond. We usually do CP on the order of, let's say, 500 microsecond. So we actually go long enough compared to the coupling strength, what it would dictate. But there's a powder averaging here. So you can actually see this effect. So we can actually see oscillations under the Goldberg CP. Looks quite nice. And so you do see it oscillating experimentally. And what is Lee Goldberg CP? Lee Goldberg CP is when I have killed the proton-proton homonuclear dipolar coupling. This regular CP, I told you that in the spin lock on the proton, there's still homonuclear proton coupling going on. And that's going to impact in some way. I have to think about exactly how it impacts, but you don't get clear oscillations usually for doing the regular CP. But under Lee Goldberg proton homonuclear decoupled situation, you get nice patterns. So you can see this. So yes, it's possible to observe in the CP oscillation something that relates to the coupling strength. And I don't remember, but I think CH bonds, something on the order of 50 microsecond is true. Maybe it's powder averaging coming in. You have to think about that. So this is kind of an isolated spin pair. And since all your molecules, they don't have the same dipolar coupling because there's orientation dependence, you won't hit a clean zero. Yeah. Yeah. So in that sense, it's different from Jacob. Take a break? Yeah, okay, good.